Hey everyone, we're going to dive further into Ørsted's discovery about magnetic fields due to current carrying wires. We remember back in electricity, we said that if you had a single charge, fell off by 1 over r squared. But if we took that single charge and stretched it out over a uniform line charge distribution, we saw that the infinite line of charge ended up falling off as a 1 over r relationship instead of 1 over r squared. Well, from our lab with magnetic fields, we saw that yes, magnetic fields got stronger with stronger currents, and we saw that as we got further from the wire, it fell off as a 1 over r relationship, just like an infinite line of charge. So Biot-Savart here wanted to know that is there a 1 over r squared relationship with just finding magnetic field strengths like we found with single charges in electricity. So they tried to come up with a correlation there, and this is what they came up with. The magnetic field strength is the sum of the contributions of all the current along the entire length of the wire. Meaning, if you look at that formula up there, we've got the mu0 over 4 pi, we've got the current and the dl being our current element. Remember, the current times the length of that wire. And we're going to cross that with the r hat being the unit vector that is pointing in the direction of the distance from the wire, and we're going to divide that by 1 over r squared relationship like we saw for individual charges. So individual current elements, they said, follow the same thing as individual charges. And if we do that, we could hopefully find why the relationship of 1 over r was found out in the lab based off this equation. So here we have a small segment of a wire that has a current running through it in this direction. So right off the bat, I can tell you that the magnetic field at point P up there is pointing out towards you. How do I know that? Because of our first right-hand rule. Put your thumb in the direction of current, curl your fingers out of the page up top, and you have magnetic field that comes out up top here and goes back into the page at the bottom here. The question is, can we use Biot-Savart's law to find the magnetic field strength at that point P based on what they said? So right now, Biot-Savart's law, it's mu0 I dl cross r hat over 4 pi r squared. Kind of like Coulomb's law, but for magnetic fields along current carrying wires. So the first thing we want to look at is if we want to find the magnetic field due to, say, this little segment of the wire back here, which we'll call dl. dl has a vector notation to it. It's in the direction of current. So the dl is to the right because the current in this wire is to the right. The r, remember r is the position from our little dl segment, our current element, to point P. So dl has a unit vector that points in the direction of r that has magnitude 1 and points in the direction of that r position vector. So you can see right now that if you look at the dl is in the I direction, the r hat is in the I and j direction. So if you cross I with j is going to give you positive k coming out of the page. So that again confirms that our direction is correct. But as we go down this wire here, just like we did with the infinite line of charge, we say we have a current element going down the wire that's going to have different dl's, and as we change the dl, we're also going to be changing the position vector, our distance from dl to that point P, and we're also going to be changing the angle theta. So we've got, again, 3 things that are changing here as we move down this line. What we need to do is write an equation here in terms of one changing variable like we did before so that we can solve for this magnetic field strength. So I'll look at that triangle that I've created for us right here. And in this triangle, there's only one thing that's constant as I move down the line. It's that height from the wire, y. So I'm going to try to write 2 equations in terms of that height above the wire. So first I'll go with sine of theta. Sine of theta there is the opposite over the adjacent, which is the y over the r value. So if I want to solve for my r, I can rearrange this and get r to equal y over sine of theta. But since I have theta in the bottom there, I can rewrite sine of theta as y cosecant of theta. But remember, I have r squared, so if I want to sub in r squared, I've got to square r and square everything in my setup there. So I can replace my r squared with this y squared cosecant squared. So now let's see if we can get rid of that dl. When I write my tangent of theta equation here, I can write it as the constant y, the opposite side over the adjacent side, negative L. And the only reason I'm making it negative L is because I'm calling the origin where point P is. So I'm going to the left of the origin, negative L. But I need dl in my equation there. So dl, I've got to rearrange this whole equation for L. And I get L to be negative y, cotangent of theta. But I've got dl in this equation, which means I've got to take the derivative of L. L just becomes dl, y is a constant, and the derivative of negative cotangent is cosecant squared theta d theta. So now I can substitute in dl for my entire dl cross r hat. One thing I can also do, since dl cross r hat is a cross product, that means that r hat has a value of 1, and a cross product means that you multiply those two vectors by the sine of the angle between them. So I'm going to replace dl cross r hat with dl sine of theta, and I'm going to substitute also in my dl. So there we go. The equation got a lot grosser, but now we can see that things will actually start to cancel for us. Get rid of one of the y's up top. We can get rid of the cosecant squared with the cosecant squared. And if we rearrange this and write this out a little bit nicer, this is what we get. I'm left with mu 0 I over 4 pi y, and I integrate sine of theta d theta between theta 1 and theta 2, being any two angles along the length of my wire. So when I do that, what you get is negative cosine of theta between theta 1 and theta 2 multiplied by all of the constants that are out front. The mu 0 I or 4 pi y on the bottom. Putting in those two values, your equation gets a little bit more stretched out, which leaves us with this. You have negative cosine of theta 2 plus cosine of theta 1. Those thetas being the two angles that you pick as you move along the length of your wire. But what about the extremes? What if I go back and I stretch out the wire to its maximum length? If I stretch a wire out to infinitely long, we can take two extremes. We can take the angle to be so far away that it's pretty much 0 at one point and 180 degrees the other way when we're so far away that we're pretty much level with point P. So your bounds can be 0 and 180 degrees, or we can put in 0 and pi for our two bounds. So if I put in pi for theta 2 and 0 for theta 1, cosine of 0 is easy. That's a positive 1. We're going to add that to cosine of pi. Cosine of pi is negative 1, but it's also multiplied by a negative, which will give us positive 1. We're just going to simplify our equation a little bit nicer into, which has a 2 on top and a 4 on the bottom, so I can simplify that one more time into this. That the magnetic field strength from an infinite wire is mu 0 I over 2 pi r. Y being the length away from the wire, which is that 1 over r relationship that we saw in the lab. So Biot-Savart's equation, having an individual current element have a 1 over r squared relationship, is true, and when you sum those up along really, really long wires, you get the 1 over r relationship that we experimentally saw. So the magnetic field due to a long straight piece of wire ends up being mu 0 I over 4 pi r multiplied by negative cosine theta 2 plus cosine theta 1, and when we put in our extreme bounds between those two segments of the wire, we get an infinite line of charge, which is mu 0 I over 2 pi r, which is the relationship that we saw experimentally in the lab. Let's apply it to a new situation. Let's apply the magnetic field Biot-Savart law to the center of a current carrying loop. So if you have a current carrying loop, how do we calculate the magnetic field at the center of the loop or along any segment of that center of the loop moving out in that z direction? So this looks an awful lot like our ring of charge, but now we have a current loop instead of a ring of charge. Just like the ring of charge, now with a current loop of charge, the question is, what is the magnetic field strength along the z-axis? Well, first thing you want to do is, you can see the current at the top of the page is coming out towards you, and then the current goes back into the page on this side of the wire. So with that being said, kind of like what we saw in the last video, put your thumb in the direction of current and curl your hands. What you're going to see is that you get magnetic field loops that look like that around the top of the wire. And if you look at the bottom of the wire, put your thumb into the page and you get magnetic field loops in the opposite direction. if we extend those loops outwards away from the loop all the way out to point P, the magnetic field strength from the top of the wire is pointing this way, and the magnetic field strength from the bottom of the wire is pointing down in this direction, if you look at the tangent of the magnetic field at those locations. So if I want to solve for the net magnetic field from the top and bottom, what I need to do is add up components. I can see that my y components, up and down, will be equal and opposite. Magnetic field in the y direction is going to cancel to 0 strength. So that means that all I've got left is a magnetic field in the z direction, and instead of taking a tiny piece of charge like we did for the ring of charge, we're taking a tiny current element from the top of the wire to point P. And we can do the same thing from the bottom there, and we can say that this angle here with respect to the z-axis is actually the same angle up here. So writing Biot-Savart Law, you get mu 0 I over 4 pi integrating dl cross r hat over r squared. Again, since r hat is in the direction of the position vector, and we're only looking at the magnetic field in the z direction here, since they are perfectly perpendicular, we're looking at the sine component of the magnetic field, which means dl cross r hat really can just give me dl sine theta over r squared. So let's see if we can eliminate some of those changing variables there. If you look at it, whether I look at the top of the wire or the bottom of the wire here, at the bottom of the wire, I'm still going to make the same angle theta that I make from above. So really, all that's changing along the way is my perspective of the wire. So really, some constants that are here for us are the distance from point P to the center of the wire, and actually the r length and the angle are all pretty much constants. So we can rewrite and get rid of the sine theta and the r squared in terms of constants. Sine of theta here is going to be my opposite side, which happens to be big R, the radius of our loop, all over r, which is the hypotenuse, and we can write r in terms of the constants that we have, the z and the radius of the ring. So I could write that as z squared r squared square root. So that would be sine of theta. If I want to put in what r squared actually is, r squared ends up being z squared plus large r squared. So I'm going to put those into my Biot-Savart law, and I'm left with this, which gets really, really gross, but now dl is the only thing that's changing. The current element along the top of the wire all the way around the entire loop. So that means I'm going to go from 0 to the entire length of that loop. So dl is just going to become L, and combining some constants here, I get mu 0 I r over 2 pi z squared r squared to the 3/2 power, combining those two z squareds and r squareds at the bottom. And L is going to be the length around the entire loop, while the length around the outside of a loop just ends up being the circumference of the loop, which is 2 pi big R. A couple things are going to be able to cancel for me. I'm going to be able to get rid of a pi, I'm going to get rid of a 2, and I'm going to be able to combine my 2 R up top. So the magnetic field in the z direction, along the axis away from a current carrying loop gives you mu 0 I r squared over 2 z squared r squared to the 3/2 power. Now what we can do is we can go to the extremes. The first question that was asked there is, what is the magnetic field at the center of that loop? That would mean if z, distance from the loop, equals 0, what does that do? Well, when you put in the 0 there, you're left with just an r squared in that bottom fraction. And r squared to the 3/2 power is really just r cubed, which means that a couple other things can cancel here. And the magnetic field at the center of a current carrying loop is mu 0 I over 2r. But let's go to another extreme. So what if z is much, much, much bigger than r? Well, what that means is that the r pretty much is going to 0 in our distance equation down here, and you're left with z squared to the 3/2 power, which leaves you mu 0 I r squared over 2 z cubed when we get to the very, very far extreme, which again shows that the magnetic field strength is dropping off by a cubic equation the further you get from a magnetic field loop. So right at the magnetic field right at the center of the current carrying loop, you get mu 0 I over 2r. When you're off center, we have that large equation that we came up with, as the magnetic field strength is in the positive z direction, since the y components cancel, and it gives you that. So what Biot-Savart we're trying to do was find the 1/r² relationship for current carrying wires, similar to what we've done with electric monopoles and charges with Coulomb's law. There's got to be a better way, and we're about to find that out next time.